So Nakajima sensei is going to give his third and last lecture on Instanton modular spaces and W-algebras. 聞こえます? I don't think he's... Okay, so Nakajima sensei is going to give his third and last lecture on his course on Instanton modular spaces and W-algebras.
Thank you very much. Thank you very much for coming to my last lecture. So I first recall what I explained at the last moment of my second lecture. So MKR is a symplectic resolution Uhlenbeck space, and it has the action of R plus one-dimensional torus, which is the product of C star square times T. T is the maximal torus of SLR, and the C star square acts on the base. And I emphasize that it's important to understand the fixed point set and MKR. If you consider this maximal torus of SLR, it's disjoint union of products of Hilbert scheme of points, and number of points is K1, K2, and KR, and the total sum is equal to K. And if you further consider the fixed point with respect to the larger torus, this bold T, then fixed point set is R tuple. Not here, so this is R tuple. And the tuple of partitions whose sum of the total number of boxes is equal to K. So in particular, by the localization theorem, equivalent cohomology of the space is isomorphic to equivalent cohomology of the fixed point after tensoring the fractional field of equivalent cohomology point. So if you tensor this fractional field, then it decomposes into tensor product of R copies of Fock space, tensor with fractional field. And in particular, each Fock space receives representation of Heisenberg algebra. So you have in total you have R Heisenberg algebras. So in other words, you have the Heisenberg algebra for R-dimensional torus, which is regarded as a maximal torus of GLR instead of SLR. So, but this Heisenberg algebra acts only on the equivalent homogeneous fixed point, which is not the isomorphic to equivalent homogeneous whole space, if we don't tensor this fractional field. So there should be some sub-algebra of Heisenberg algebra, which should preserve this integral form of the equivalent. So it should be not. It should be defined over the genuine equivalent homogeneity, not after the localization. Okay. So one series of elements is easy to define. So this is already done long time ago by Baranovsky. So let me explain this. So it's almost similar to the case of Hilbert scheme points. So consider mk plus n r and then kr times C2. And if r equal 1, this was the Hilbert scheme points, and I define some corresponding Pn. So this definition, I will not explain how we can define it, but exactly, if you know that the definition of the MKR in terms of geometry as a frame, the modular space with ocean free sheet, exactly in the same manner you can define Pn. This can be defined. Then you have the map to mk plus nr and mk n kr cross C2, and both are proper. So then, in the same way, you can define Pm. So I only use the case when alpha is equal to fundamental class of origin. So you can define analog of Heisenberg operator in the case of Hilbert scheme point. Then Baranowski proved following. So this is again Heisenberg, satisfy the Heisenberg relation. But the level is different. So this is R times M times delta M plus N. So it means we get the level R Heisenberg. So this is roughly, you need in a certain justification, but basically this corresponds to the diagonal Heisenberg subalgebra in the previous R-dimensional Heisenberg algebra. Then each factor commutes. So because of that, the diagonal Heisenberg has level R instead of level 1. Okay. So in particular, so this direct sum, it's the T of MKR is a representation of Heisenberg algebra. But the irreducible representation has the same size with level 1 case. So this cannot, because this is a tensor of R copies of tensor product of R copies. So this is much bigger than irreducible one. But at least so you have this decomposition. So Fock space for this Heisenberg. And tensor with some multiplicity space. And in fact, this has a geometric realization understanding. So this is isomorphic to the so-called equivalent intersection cohomology of the Vertex space. In that sense, because as I emphasized that if the group is not different from SUR, we can define Uhlenbeck space, but we cannot define the analog of MKR. So this is a special feature in type A. So we actually want to understand this intersection homoalgebra in the Uhlenbeck space in general. So this Baranovsky's result says that starting from M, then you consider this Leibler-Heisenberg algebra, and somehow you should understand the summand which multiplicity space, which is somehow orthogonal, or how to say. This is a tensor product, so it's not also orthogonal, but this, you must understand this multiplicity. And the AGT conjecture, AGT correspondence conjecture that this should be. A representation. Oops. There it is. So my program somehow. Somehow, yeah, my program stopped working. Sorry, could you wait a little bit?
No problem.
I don't know why. So let's see. Maybe I need to reboot my computer. It doesn't work.
Okay, no problem.
Let me try. Maybe it works now.
Yeah, we can see your screen now.
Okay, that's good. I hope it doesn't happen. Okay. I mentioned that this should be a representation. Oops. Okay. So we want to show this statement. And in fact, there are two approaches. So one is due to Schumann-Bass law. And also Fagan-Timboric. So I mentioned the tautological bundle. Yesterday. So this is vector bundle over MKR. And then you consider its first chunk class. So this is the equivalent cohomology class. So this is H star of MKR. So you consider this as an operator by coupler. So the correspondence changes the Instanton charge K by this definition. So this compared with this first chunk class of tautological boundary has very different flavor. So this is a just a cup product. So it sends equivalent cohomology of MKR to itself. Okay. So this preserves the Instanton charge. But anyway, so this is the operator. And you consider then and again. I don't know. Okay, maybe I give up to continue this writing. So I think I have a note to which I prepared for this lecture. So I will just read. Okay, it is more reasonable, I guess. Okay, I mentioned that so there are two. Let me see. So do you see my cursor? Maybe you don't see. Gradually see cursor. Okay.
Yeah, we can see.
So use this first chunk class of the tautological bundle and particular correspondence P of plus minus one. So I define the correspondence for M and N, but this plus minus one has some very special feature that this correspondence is non-singular. So this is smooth. And somehow this smoothness is important because they basically use localization theorem, finer form of the localization theorem to compute everything locally. So then the computation becomes combinatorial. And they can understand the commutation relation between the composites of those pairs of operators. And then they observe that, in fact, these two or three operators generate the so-called Yangian of affine GL1 hat. So I hope most of you all heard about the Yangian for the finite dimensional simple, complex, simple Lie algebra. And there is some analog of this Yangian for the affine Lie algebra. And this is a particular case of the Yangian for the affine GL1. So it is, as I said, it is somehow generated by those three operators. And it contains, it is a very large algebra. It contains, for example, Virasoro algebra. So this is given by the commutator of this first Chern class and field plus minus. So this is the first Fourier mode of Virasoro algebra. And once you have this first Fourier mode, then you take the commutator of this first one and Heisenberg. Then you get the second Fourier mode, P of plus minus 2 as a commutator. And you just continue. So you can generate all the elements by starting from those two. All Fourier modes, for example. Yeah. And then so these three operators generate large algebra, which is Yangian for GL1. And double algebra, and this maybe I should emphasize, this Yangian for GL1 hat is independent of R. So a priori this MKR depends on R, of course. And this double algebra is the double algebra of GLR or SLR. So it is really actually depend on R. But Yangian for GL1 hat is independent of R. So it's a kind of limit of the double algebra when R goes to infinity. And anyway, so in fact, it is easier to define somehow, easier to define Yangian for GL1. And then you recover the double algebra as the quotient, its quotient. Okay. So this is an approach by Schiffman, Basman, Fegin, Paulo. Okay. But this approach is very specific for type A. For example, so if for exceptional group, there is no limit and nobody knows what is the counterpart for the Yangian for GL1 hat for exceptional groups, for example. So for classical group may be possible, but anyway, I think even for classical group, nobody write down what it should be the limit of double algebra. So Moiko Kunkov, so they consider the type A, and Bremer and Finkenberg and I study in general for general group in a different method, by a different method. So double algebra in general, so double algebra for type AD is defined as the reduction of the affine algebra. And this is the definition of the double algebra, but nobody understands how to realize this reduction in a geometric way. So we somehow need to use alternative description of double algebra. And for Taipei, this, we are lucky and we can use alpha Yangian to realize double algebra. But this construction doesn't work in general. So instead, and also, maybe I should also say that in general, double algebra has no presentation, like how to say, workable presentation, like generator and relations. So you must use some way of understanding of the double algebra, which can be realized in geometry. So luckily, so we can use the Feigen-Frenkel's characterization of realization of the double algebra. So I hope, so you know this Feigen-Frenkel. Maybe Arakawa-san will explain that in a few weeks later. So anyway, I just briefly recall what it is. So you start with simple real algebra. So I assume G to be IDE, but their construction is more general. And T is a carbon subalgebra. Oops. And alpha I is a simple root. Then, so in Heisenberg algebra, so for each alpha I, so alpha I determine the SL2 subalgebra isomorphic to SL2 in G. So corresponding, so you have the Virasol algebra, right? And by Feigen-Fuchs realization, Virasol algebra is a subalgebra of Heisenberg algebra. And you tensor this Heisenberg algebra for the perpendicular to the alpha. So then this tensor product can be understood as subalgebra of the Heisenberg algebra of torus, this carbon subalgebra. And you consider this for each I and take intersection in Heisenberg. Then it becomes double algebra. And for this statement, in the original paper of Feigen and Frenkel, they consider the case when the level is generic. And we want to understand the equivalent, as I emphasized several times, we want to understand the genuine equivalent model, which is defined over polynomial ring. And the generic level means that we tensor with fractional fields. And once we've tensored with fractional fields, many interesting features of the genuine equivalent homology will be lost. So we don't want to do that. But somehow, in this particular case, you must just carefully look at the argument of Feigen-Frenkel. And in fact, the argument can be run over polynomial ring. And I just said this is just simply said this is inclusion. But in fact, more precisely, we first need to define everything over polynomial ring and take intersection over polynomial ring carefully. Anyway, so this part is written in my paper with Bremer and Finkelberg in the appendix. This is our paper is basically geometry or geometry paper in geometry, but in the appendix we just carefully explain the Feigen-Frenkel over polynomial. So we want to realize this refinement of Ekeren-Frankel in a geometry. So for that, we need two things. So one is, of course, realize this picture. So this kind of alpha I and corresponding Chiral algebra and so on. And also, we must construct, this characterization, use Chiral algebra. Intersection of Chiral algebra is double algebra. But we first need to understand Chiral algebra. But it means that we just need to understand the SL2 case. And as I already indicated in the first approach, somehow Chiral algebra is relatively easy to understand. And anyway, so this is the type, fortunately, this is type A, right? So even if we start with arbitrary AD group, if we restrict to pick up a particular simple root and consider corresponding the subalgebra, okay, then it is SL2. So it's always type A1. There is no type B2 or B1 or C1. Okay? So because of this, you only need to understand type A case, and the first approach can be used, for example. Also, there are many other approaches for Chiral algebra. And as I mentioned, this Heisenberg algebra. The SL2 case is basically we just need to understand. We just need to realize Fading-Fuchs construction in the geometry. So this is possible. And I will not explain the second part. So I will concentrate on the first part, 2A, how it is realized in a geometric way. So any question or comment? So if not, let me ask. Let me continue. Okay.
Hi, I just wanted to ask about this Feigen-Frankel method. Is it at all related to the Moreau transform?
Yeah. This is Moreau transform. It's just people. Some people call this Moreau transform. Yeah, I hope that Arakawa-san will explain in his lecture series. Or no? So anyway, I think this is some basic in W-algebra. It's, for example, it's written in the textbook of Benjamin-Frankel. Okay, so very roughly, this is somehow very, how to say, in a geometric approach to this kind of picture is somehow manifest. So this is a 0th step of this geometric realization. So let me again consider MKR, and I emphasized again that there's R-dimensional torus action. But now I consider the smaller torus, Ti. So that is, so I pick up i's sister and I plus 1's sister, and I replace this 2-dimensional torus by 1-dimensional one, which is given by the diagonal. And if I consider the fixed point set with respect to smaller torus, then fixed point becomes larger. And in fact, it's not so difficult to understand it. Yeah, of course, I don't to explain the detail of the space, but if you use MKR as modular space, this statement it becomes manifest. So fixed point set is again some product, and instead of all Hilbert scheme of points, so what you get one piece which is correspond to R equal 2. So we have R copies of Hilbert scheme points, but I factor and I plus 1 factor corresponding to this choice of torus. So I and I plus 1 factor are replaced by this rank 2 modular space. And if you further take the torus, this T, maximal torus, then this two-dimensional torus is replaced by Hilbert pairs, product of Hilbert. So in this way, somehow you see that so MKR contains rank 2 modular space inside. And as I said, rank 2 case correspond to Chiral algebra. And you consider, you change various I, then somehow this rank 2 factor moves around. So somehow you expect that you can say something on MKR. Okay, so this is the 0 step for realizing this kind of realization of the double algebra inside Heisenberg algebra. But unfortunately, so this is a fixed point. So you have a pullback homomorphism from here to here. So the upper space to lower space. And also, so this is further embedded in MKR. So you have the corresponding pullback homomorphism with respect to these inclusion. So starting from equivalent homology of the whole space, you can have equivalent homology to this space and further to this. And as I said, this is a representation. The final one is a representation of Heisenberg algebra. And the second one is a representation of the product of Heisenberg algebra and Chiral algebra, because we have one rank 2 modular space. So it looks fine, but in fact, if you do a little bit of computation, you immediately see that this is not actually correct space. It is pullback by the inclusion of the pullback homomorphism with respect to inclusion is not correct, doesn't give correct subspace in the Heisenberg algebra. So even in rank 2, so this, if you just consider this red part and compute what is a pullback, and you see that this doesn't correspond to Feigenflex construction of Chiral algebra. So this is not correct. And in fact, this is the whole point of the subject for new development of the recent, or starting point of the relatively new development of this geometric representation theory. So this is what Moreau and Gukov introduced, called the stable envelope. So instead of naive inclusion, so you do something more sophisticated. And afterwards, I realized that this stable envelope is closely related to the so-called hyperbolic restriction factor, which was introduced by Braden. So those two are some sophisticated tools in geometric representation theory. And it's not my purpose to explain those tools in my lecture. So several years ago, I explained those in Park City conference, and that is the lecture note it was published from AMS. So if you are interested in such tools in geometric representation theory, then please look at my note. So instead, I just briefly explain what kind of construction it is. This, I mean, of course, this, in order to give the precise detail, I need to prepare lots of things. So I really just sketch the construction. So one point is not only the considering the torus action, I need to choose co-weight in the torus, so or one parameter subgroup in the torus, which is generic in the sense that the fixed point set remains to be the same. So in the space of such one parameter subgroups, so there's analog of wire chambers such that if one parameter subgroups sit in a root hyperplane, then the fixed point set becomes larger. But if you avoid those hyperplane, then the fixed points are unchanged. So it's like some point in the interior of wire chamber. So anyway, I choose such one parameter subgroup and consider the attracting set. And this is a crucial point. So this attracting set is a Lagrangian subvariety in a certain, not certain, in a product of the whole space and fixed point set. And this attraction set is a natural object to consider because it's like that. So anyways, I cannot go much detail. So attracting set is just point in this space such that this has limit under this one parameter sub flow by the one parameter sub. So I wrote this picture. So this is a picture when MKR is the cotangent bundle P1. So I have this red line, so this is T star P1. T star C1. So this red line is C1. And if you take a point in the CP1, so then it stays in CP1 by the flow. So particularly it has a limit. But you also have other point, like in this black line. So this is a inverse image of the axis. So this CP1 is a resolution of C2 divided by plus minus 1. So you consider the west. This is algebraic geometric set strict transform of X. So you have axis in C2 modulo plus minus 1. And then you take the inverse image. Then it flows to north pole of the node CP1. And all other, so the flow, this gray arrows shows the direction of flows. If you start with other point, then it go away, like here, and go to infinity. So it doesn't converge. If it, I mean, maybe it's more simpler to consider the case of C2. And the flow is, sorry, maybe X, Y is confusing. So Z1, Z2, and you multiply T and T inverse. So in order to have a limit, so flow goes like this. So it has a limit if and only if this Z2 is equal to 0. So namely, you have this x-axis as attracting set. Then this stable envelope gives isomorphism between the equivalent homology of fixed point set and equivalent homology of the attracting set. So this is not simply, so fixed point is of course fixed, so it is subset in the attracting set. But this is not simply the inclusion. And this, I mean, this inclusion becomes isomorphism after tensoring the fractional. But it's not what we want. We want to do everything over polynomial ring. And the stable envelope is not just given by inclusion. This is more associated with construction. So anyway, so this the two isomorphism. And we further compose with a map to the whole space. So this corresponds to this left side corresponds to Heisenberg algebra, and this should be the double algebra. So it goes in the opposite way. So we want to realize double algebra as a subalgebra Heisenberg. So this corresponds to the transpose of the inclusion. Or maybe you instead you consider the ordinary instead of Borel-Moore homology, you use ordinary equivalent homology. Then you have map in this direction. Or maybe not in here. Oops. And again, as in the 0th step, which I explained here, you can also take one parameter subgroup in this smaller torus to realize the relation like in the case of Virasoro algebra. Right? Maybe I don't write this. I just don't write this. So I take Ti, smaller torus, and take one parameter subgroup and consider the stable envelope. And there are some relation between this stable envelope and stable envelope for rho. So rho I is contained in a chamber, contained in the root hyperplane, which should be the adjacent to this wide chamber which contain rho in interior. So rho I is sitting in the boundary of chamber. Then you can relate the stable envelope for rho I and the stable envelope for rho, like in the 0th step, like this. So in this way, you can realize Feynman-X construct. And for type ADE, as I said, you cannot use this space MKR, so you must directly work on the Uhlenbeck space. And this is singular, so you must use the so-called intersection homology, equivalent intersection homology. But this, I mentioned that this stable enthalpy has close relation with the so-called hyperbolic restriction factor, which is defined for intersection homology. So you use those tools in geometric representation theory to generalize this picture to ADE. So in this way, you can realize Rayleigh-Fuchs construction in the geometry. So there is one point which we crucially use G to be ADE group. So up to now, so I think that most of the explanation should be applied to more general case, including BC, FG types. But in fact, it's just I skip an important part because somehow this understanding Moreau I is not, unfortunately, understanding Moreau I is not enough. Somehow it corresponds to the computation, it corresponds to the intersection inner product of alpha I and alpha J. So that is corresponding to Cartan matrix. And for AD group, the Cartan matrix, diagonal entries are 2, and off diagonal entry are 0 or minus 1. So in that sense, it's similar to the case of SL3 type 8. But if you start to consider type B or C or F or G, then rank 2, you have additional rank 2 case, namely B2 and also G2. And that case are not type A, so you need to do some computation, but we cannot do that for type B2 or G2. That's the reason why we cannot do more general groups. And also, expectation is that we don't get the double algebra, genuine double algebra for the case of BC, FG. So in fact, we should get some double algebra which should correspond to twisted affine algebra. And I'm not sure so people do understand the twisted version of the double algebra. So this, anyways, I think that the Feigen-Fuchs result is about genuine double algebra, not twisted one. So somehow we still need to do lots of things in general. So that is the reason why we need to achieve that. Okay, this is a little bit brief, but this is my explanation of our proof of the HET conjecture for general groups. So if you have any question, please ask this at this moment. Okay. Okay, then let me continue. So we consider the higher level case. So this is a work in progress with Nakajima. But unfortunately, maybe we have stuck so at some point, I mean, we believe that we almost have a proof, but somehow we are lazy to finish the paper. So I hope this is not the actual mathematical problem, but somehow we cannot proceed recently. Anyway, so what do I mean by higher level? So we consider the Instanton, framed Instanton on S4, or maybe so S4 is the R4 1-point compactification R4. So we want to consider more general Instanton on this quotient or overflow space. So instead of R4, we consider the quotient by this cyclic group. So zeta is primitive L root of unity and acts in this way. So this is type A, L minus 1 singularity. Formally, you could consider more general type AD singularity. So I hope you heard about there's a classification of a finite subgroup of SL2 corresponding to a linking diagram. But somehow we think that type A case and the other type case are somehow different, and type D or type E case are much more difficult. And anyways, I hope you will see that why type A assumption is crucial in the following discussion. Okay, then expectation. I mean, this is maybe physicists already say this is well known result, but mathematically this is still not established. So we take a compact simple Lie group K, and we consider K Instanton modular space on precisely we consider the 1-point compactification and consider framing, like in the case of R4. This Instanton modular space is a special case of the so-called Coulomb branch of framed affine Kuba-Base. So I don't want to go, I mean, Arakawa mentioned Coulomb branch in his lecture, and maybe some of the audience are interested in Coulomb branch, but if I start to explain Coulomb branch, it takes I need too many preparations, so anyway, so the theme of this lecture is somehow I don't explain the detail of modular space, and just I mention the properties. That is my theme. So even for Coulomb branch, I don't want to explain the detail. So anyway, so this you have modular space, and we have some larger family of spaces, which is strictly larger. And the index set for K Instanton modular space for R4, if you forget this finite cycle group, then it was just the integer, non-negative integer, that was called Instanton charge. So analog of the Instanton charge for the Coulomb branch is a pair lambda mu. So lambda is a dominant co-weight. So maybe I should explain what is in my convention K of affine. So we consider complex simple real, maybe something. So I start with K of SU. 2. Then this is, oops. This is a real algebra. Somehow the program doesn't work. So this is to a file. Complication. That's it. So lambda and mu are the dominant coweight of the affine real algebra, and dominant coweight and coweight. Mu is a coweight which is smaller than or equal to lambda in dominance. And even for level 1 case, this inclusion is strict. So if L equal 1 case, so I take lambda to be zeroth fundamental, where I use the notation for weight instead of co-weight. But somehow I implicitly take the Lagrange dual real algebra and consider weight. Because as I explained soon, so this is related to the representation theory of the Lagrange dual. So anyway, so this is the zeroth fundamental co-weight, and the Uhlenbeck space which we have been considering, indexed, labeled by the non-negative integer k, is a special case of Coulomb branch with this choice of the co-weights. So lambda is equal to lambda 0, and the mu is lambda 0 minus k times delta. Delta is, well, delta is again weight, but please confuse weight and co-weight for Lagrange dual. So lambda 0 minus k times delta. Delta is primitive positive imaginary root of the dual affine. So you can subtract more general linear combination of roots. So but k times delta is a very specific choice, right? Mu could be modular. So it means I explained the Uhlenbeck space as partial complication of moduli space of instantons on S4, and K is I said K is topological charge. For example, if K is SUR, that is the second Chern class of the bundle. And on S4, there's no other topological charge. So the Coulomb branch is modular space, is supposed to be modular space of instantons, but it should be instantons on more complicated space. So I don't want to explain what kind of complicated space we are considering, but it's again non-compact and somehow topological. The counterpart of the topological charge, K, is more complicated and corresponds to pairs of co-weights. Okay. And in fact, this complication is exactly corresponding to representation theory of the Lagrange dual affine algebra. So this complication is very good. Okay, let me continue. And this space is, although we have more discrete data, but more larger family of spaces, the property is very similar. So we have the torus acting on the same size of torus acting on the space. So this maximal torus of complication K times C star cross C star. But in fact, it is more natural to consider T cross C star as a maximal torus of the corresponding. I said K affine in the real algebra, but I consider the corresponding group and its maximal torus. Affine Katsumuri group and this is the torus. And the C star. or maybe if you want to include the C star for the degree operator, that you could include also. But it acts on the space trivially. So this is actually maximal of the corresponding Katsumori. And this C star cross C star originally acts on the base. So this acts on C2. And for level 1 case, and this is the 0 minus k delta. So this one piece of C star is not really actually one factor. So this is a hyperbolic C star. So xy is sent to t times x, t inverse. Okay. In a sense, this preserves the symplectic form, and it is better to distinguish the group which preserves the C star symplectic form, which doesn't preserve this. And then, so this Coulomb branch is conjecturally related to the representation theory of the affine Lagrange dual affine reals. So this conjecture geometry Satake was formulated in my joint work with Bremer, I think. So first, the geometric property is this fixed point. So this is analog of Uhlenbeck space. So this is singular one. So what I mean by analog of Uhlenbeck space. So for type A, I mentioned that we have Uhlenbeck space and its symplectic resolution, which we have been denoted by M of KR. But this MC is analog of U, Uhlenbeck space. And in that case, if you take the torus fixed point, and if I put this also this hyperbolic C star, then fixed point set becomes just a point. And more generally, for lambda and nu, so it could be either point or empty set. Sometimes it becomes empty set. In fact, this is empty set if and only if the corresponding weight space of the representation is 0. So in that sense, we have complete understanding when it is a point and when it is empty. So representation is realized using MC as follows. So again, we choose one parameter subgroup, like in the case of stable envelope. But now we take co-character in T of affine, not T, in larger T. And we take sum. So this has Weyl chamber as affine Katsumori group, and we choose some dominant one. Then we take again the attracting set, and we first consider non-equivalent. So there's no T here, right? And this is a Lagrangian subvariety in MC of lambda, and we take the top degree cohomology, the top degree volume homology, spanned by fundamental cycles of this attracting set. In fact, it is more, we first consider intersection homology of this Coulomb branch, and we apply the hyperbolic restriction function. And it becomes vector space. And this is more precise definition of this top degree volume homology of this attracting set. But in fact, at the end, this is isomorphic to hyperbolic restriction. So I write in this way. So the main statement is, so this vector space, so this is not the equivalent one. So this is just the usual homological. So it is a complex vector space. We take direct sum. So this has a structure of the dual affine D algebra. And this mu part, direct summand of this, is corresponding to weight subspace of the integrable highest weight module with highest weight lambda. So lambda is dominant weight. So recall here, lambda is dominant co-weight of the affine algebra. So we are considering the dual Lagrange dual D algebra. So lambda is dominant weight of the Lagrange dual D. And mu is a weight of Lagrange dual D. So this summand, top degree part of the attracting set, is weight of space pre mu lambda. That is the state. And moreover, this representation is compatible with the restriction to Levi subalgebra. So I briefly mentioned that. So in the AGT, proof of the AGT, so we consider rho in generic co-character rho in T and also rho I in Ti. And that corresponds to the Virasoro subalgebra in Heisenberg. And as an intersection, we realize double algebra. But here, it's much simpler one. So this is a co-character in the affine torus of the maximal torus of the affine algebra. So the chamber, this chamber is not the chamber in the finite dimension torus. So this is a chamber in the affine. And I take a dominant chamber. And the boundary is a root hyperplane corresponding to simple root of the affine algebra. And I consider the corresponding Levi subalgebra. And again, like in the case of the AGT, so those stable envelope or this hyperbolic restriction factor is compatible with rho affine in the dominant chamber and rho I corresponds to boundary of the dominant. And that relation among hyperbolic restriction correspond to restriction of this representation of the affine algebra to Levi subalgebra. Yeah, this Levi subalgebra is Levi subalgebra as a Katsumudi algebra. It's not affine Katsumudi algebra of Levi subalgebra of finite dimension real. So if instead, Coulomb branch can be defined for any choice of the group and its representation, but here we just briefly mentioned this. We consider the framed affine quiver case. So we take affine quiver, but instead we can take the finite type quiver, so this AD type quiver. And if we do consider the same kind of construction, then you recover the usual geometric static correspondence, which is proved by many people, Lustig, Ginsburg, and Markowitz-Piron. So this formulation is most close to Markowitz-Piron's formulation. So this is not, so in that case, this is not a conjecture, this is a statement. And we just see that this Markowitz-Piron's construction does make sense, if we just replace the, I mean, Markowitz-Belonen used affine-Grassmannian. We just replace affine-Grassmannian by these Coulomb branch. Their construction doesn't make sense in the affine set, or even custom set. So our point is, by this replacement, the geometric set can be generalized to hyperplex, more general setting of Katsumuri. So this is our state. This is our conjecture. And in fact, this is proved in affine type A. So we believe that this is true. So now let me try to explain the relation between this construction and VOA. So this is the usual construction of the representation of affine algebra, and it's integrable representation. So now we replace ordinary Borel-Moore homology by equivalent homology. But for this attracting set, maybe I so more precisely, as I said, we should use hyperbolic restriction of the intersection homology. So this is very simple one. So even if you consider the equivalent homology, it doesn't change much the answer. So you just replace the weight space with its tensor product with equivalent polynomial ring. So this is not so much different from the integral representation. But our actual interest is not this homology of attracting set, the homology of the whole space or ordinary homology of the whole space. So in fact, because this is singular, so we must use intersection cohomology and its cost. But somehow, if you imagine that this MC is smooth and something like M of KR, this is equivalent homology of the ordinary equivalent homology. So I use this rotation with quotation mark, but for more precise statement, we must use the cost of intersection. And then you have a homomorphism from this costoc to hyperbolic restriction. And by analog the localization theorem for intersection homology, this becomes isomorphism over if I tensored with fractional field of equivalent homology point. And in particular, for then equivalent homology, this is injected. So this is a sub-algebra. Sub-module of this weight space of the integral representation tensor with equivalent homology point. Then the conjecture which we made is the following. So this submodule of this equivalent homology of attracting set has representation theoretic characterization. So maybe I should also say this is based on a similar statement. finite dimensional system. Proved by Ginsburg and Leach. So what is the representation select calculation? So we take this integrable representation V lambda and tensored with the so-called universal asymptotic Balmer module. So this is mu. Mu is this mu. And take the invariant with respect to the Borel part of the corresponding Lagrange dual Katsumi. And this subspace is closely related to cosette field. And this can be regarded, in that sense, this can be regarded as analog to AGT in higher level. So what is universal asymptotic Balmer module? So this is a bi-module of equivalent module, polynomial equivalent module point, and asymptotic form of universal enveloping algebra out of the D algebra. So this H bar corresponds to epsilon 1 plus epsilon 2. The previous notation. And instead of the usual universal enveloping, I put H bar in here. Or this is this with algebra correspond to the filtration of the universal enveloping algebra by order of differential. So anyway, so this is almost like the Balmer module, but the highest weight is regarded as polynomial in here. So this is the formula. So if I multiply the highest weight vector by A from the right side, A is from here. When the A is the element in the affine Lie algebra, Cartan of the affine Lie algebra. And then you have this point. So anyway, so this is Balmer module, but defined over polynomial. And this submodule of the ordinary homology group of the Coulomb branch in the equivalent homology of the attracting set is isomorphic to this submodule. Yeah, so maybe I should also, yes, maybe I should also explain this arrow, corresponding arrow in the representation theoretic side, but somehow I don't remember how it is constructed in my heart now, so maybe I skip it. Anyway, so there is some simple construction from here. So now, somehow we believe that this formulation is, in fact, somehow simplified the proof of AGT even for level 1 case, and it works for higher rank cases. That is because, as I emphasized there, somehow, so this is compatible with Levy subalgebra, but this is a SL2, not affine SL2, or Virasoro subalgebra in the Katsumi-Diri algebra. So we start with the affine Katsumi-Diri algebra and pick up a particular vertex and consider the corresponding the subalgebra, which is finite dimensional SL2. So Virasoro algebra and or affine SL2 is much more complicated than, certainly much more complicated than finite dimensional SL2. But somehow we treat this affine algebra as a Katsumori algebra and corresponding Davis subalgebra. We only get the finite SL2. That seems to be simplified. So anyway, we prove, well, we don't prove it, but we plan to approach this conjecture by the following idea. So we have this map from geometric constellation, and we establish a horizontal isomorphism by geometric Satake. And as I said, we have map like corresponding mapping representation series. Then this is birational. You can also show that this becomes isomorphism after tensoring fraction. So you can consider the composite by composing the inverse of this homomorphism. But that is defined only after tensoring fractional field. So actual statement, so existence, because we have three maps. So and also this is isomorphism after over fractional field. So if such isomorphism exists, that must be coming from those composite. So the actual thing which you must check is that this composite is in fact defined over polynomial, not, you don't need to tensor this fractional field. That is the actual statement. And once you understand in that way, so this is a rational map. So if you, and also you know that possible pole of this rational map is just only on the root hyperplane. And if you check that there's no pole at any root hyperplanes, then you are done. There's no pole. So you need to check that this composite extends across all root hyperplanes. So this. And as I said, this root hyperplane is basically SL2 finite dimensional system. But in fact, there's also one imaginary root hyperplane in this, because this is affine. So you must also check the statement corresponding to imaginary root hyperplane. But somehow, then it means that so corresponding geometry is something corresponding to Heisenberg algebra, because imaginary root. Davis subalgebra corresponds to imaginary root hyperplanes, basically Heisenberg algebra. And Heisenberg algebra corresponds to symmetric products and Hilbert scheme points. So in that case, somehow we have a complete understanding of those spaces, because this is basically Hilbert schemes, and my old result says that this homology of those Hilbert scheme can be completely understood by Heisenberg algebra. And all others are finite dimensional SL2. So by the usual geometric Satake, and in particular this statement from Ginsburg and Leach, we have the corresponding Heisenberg. So by combining these two, so we can establish that this composite is free of pole. And this argument is in fact very general. I mean, at least work for the affine algebra. And once, if you prove this geometric Satake, then we hope this argument basically goes So we don't need any additional statement. So now I come back why we need to assume this surface is of type AL. And this L appears in geometric Satake as a level of lambda. Maybe I see. So this L is level of. So from the beginning, the level is a positive integer. And in order to have geometric Satake statement, so we cannot replace this type AL by other groups. So for type D or type E, so this somehow level rank duality is in behind, and if we replace this type A singularity by other singularities, we lose corresponding those even combinatorial level, we lose the correspondence with those weights of the affine. So even the statement, we still don't, we even don't know what should be the statement for geometric Satake for other type of groups. So that's the reason why we really need to assume type characters. And the other case seems to be much more difficult. Okay, thank you very much for attention. So this is the end of my talk. So any question?
Hi. So about the relationship between the Schiffmann-Vassereau and Mollico-Kunkov constructions. So as you probably know, they also find the affine in Mollico-Kunkov by, they construct R matrix with using stable envelope and then have this kind of RTT presentation. Is there a kind of conceptual reason why that algebra is the same as the one that Schiffmann-Vassereau construct?
I'm not sure it is known to be the same. And Schiffmann-Vassereau, I don't carefully study the relation. Maybe for the affine case, maybe it could be known, probably. But somehow the argument is, Mollico-Kunkov's definition is somewhat abstract, and in Schiffmann-Vassereau's definition is basically by generator and relations, and a priori there is no reason why that Mollico-Kunkov's the affine is isomorphic to Schiffmann-Vassereau's. Maybe a priori, I think the Mollico-Kunkov could be larger. Because, so in order to understand in order to show that the Schiffmann-Vassereau's affine is contained in Mollico-Kunkov's Yangian, so you just need to check this is true for generators. And that is not so difficult. But actually, so you must also show that Mollico-Kunkov's affine is not larger than those generated by generators. That is requires some check. And I'm not sure anybody do that. And for finite type case, so Mollico-Kunkov construction recovers the usual Yangian. And that is, even that, I think that statement probably can be checked by using earlier works by myself and Baragnolo. But anyways, I'm not sure. So a priori's molecular function definition is a little bit, how to say, not explicit. And that their construction is by RTT, and they must show that how big it is. And in some cases it is possible, but in general it is a difficult question. I'm not sure I know the status of this statement. Maybe for the affine algebra it could be known, but I'm not sure.
Thank you. One more question. Is it known, is it known the quantizations of the Coulomb branches for affine quiver gauge theories?
Coulomb branch of what is the question? So there is a definition of Coulomb branch.
Right.
Identification with what?
Well, for example, so in like the finite case, maybe I'm not sure the exact generality, I think you proved that they're truncations of shifted Yangians. Is there, for example,
this is a quantization. This is a problem for quantization. So you are asking the
quantization
for the
of the
quantization
affine.
of the affine.
Yeah, exactly.
I mean, the construction of homomorphism works in general. So you have the homomorphism from the shifted affine Yangian to the quantization of the Coulomb branch. That is, I mean, for type A11, maybe we need to check more relations. But otherwise, the relation is the same as the case of finite type. So the construction of homomorphism is by generator relations. So this works for affine case. But for truncation, that is slightly different. And also, you also need to know the size of the quantization. And in order to know the size of quantization, we use that the ordinary Coulomb branch, this commutative ring, has certain size. And for affine case, such a statement is known only in type A. And even I don't think type A we can prove that this is truncation of the. I mean the subject. I'm not sure subjectivity is known. Maybe we can prove some statement, so something is known, but I'm not sure.
Okay, thanks.
I mean, of course, I mean it is expected to be true, but maybe the detail is remain to be done. That is what I know.
One follow-up about that. So those algebras maybe sometimes have VOA structure, like truncations of affine Yangians. Is there some relation to what you were explaining here, like maybe via Hikita or something like that?
Let me see. I'm not too sure. So maybe, I'm not too sure this. I mean, for finite type case, this quantization of the Coulomb branch is truncated, shifted Yangian, but in fact, this in type A, this is a finite double algebra. But for affine case, I'm not sure it's related to the usual double algebra. Or I mean, it's corresponding to more general nilpotent element. I'm not too sure this is true. So truncation of the affine Yangian, I'm not sure it's known to be related to the usual double algebra. And anyway, so this quantization is very different from what I have been discussing. So I'm considering the Coulomb branch and not the quantity. I don't consider its quantization. Instead, I'm considering the intersection cohomology of the ordinary Coulomb branch. I don't have any conceptual understanding between the relation between two, but I think that there are some so people consider some kind of relation, but it's not precise and also not directly related to quantization of the Coulombs. But you should rather consider the Grothendieck ring, Grothendieck group of the representation of the quantization. So this is a replacement of intersection cohomology of the ordinary Coulomb, right? So you should not confuse with quantization with the category of representation of quantization. And also, so I crucially use, I don't consider single Coulomb branch. I consider the direct sum of over all mu. That is crucial in this construction. And the quantization is something to do with alpha Yangian, but this statement, you don't need to take the sum over mu. So I think that we don't have clear understanding of relation between two. So for me, that it seems this is just a coincidence.
Okay, thank you.
I don't think there is some.
Is there any other questions? So the conjecture is proved for level 1 case?
Probably by combining results of Arakawa and others of this coset VOA and W-algebra may be true, but I don't know. So as I said, except our laziness, I'm not sure what is obstacle to prove this conjecture for type A. I mean, for geometric static is the most difficult part, as I said, and this is already proved for type A.
Is there any simple relation between the stable envelope in the previous construction and hyperbolic induction in the new construction?
They are closely related, and I mean, so stable envelope is defined for smooth space, but hyperbolic restriction is defined for intersection homology for singular space. But they are closely related. So there's a precise relation between them. So they are essentially the same thing.
So essentially the same.
Mm-hmm.
Okay. Any other question? If not, let's thank the speaker again for the wonderful lectures. So we resume at 10.